We learned from molecular orbital theory that every time you combine two atoms' atomic orbitals, they'll make the same number of molecular orbitals. This concept holds true for metals as well, but there's so many different metal atoms connected together that their molecular orbitals start to overlap. They form bonding and antibonding orbitals that are really more like one band of space. So we call the place where the valence electrons usually hang out the valence band, and the antibonding orbitals, those empty spaces, the conduction band. The energy difference between the bonding orbitals and the antibonding orbitals is called the band gap. In metallic solids such as copper, the valence band, where the electrons are usually located, is so close in energy to the conduction band the energy difference between the valence band, where the electrons are, and the conduction band is so small in metals that it's very easy for an electron to be excited into this orbital that basically is empty. It has no space. That's why it's so easy for electrons to produce electric conduction, for electricity to flow in metals, because these electrons can jump into this empty space and zoom along the metal. In a semi-metal like silicon, the valence electrons exist in a valence band, and a conduction band is much more separated than in a metal. It's got a significant enough band gap that the electrons don't flow freely, but they're still close enough that when a semi-metal warms up, that the electrons can jump up into that conduction band. You can make a material like silicon more conductive if inside the piece of silicon you replace some of its silicon atoms with an atom that is similar in size but has a different number of valence electrons. In this model, you can assume that the silicon atoms are the gray ones. Silicon generally has 4 valence electrons, and if I replace it with an atom of similar size, but with more valence electrons, like arsenic, for example, arsenic has 5 valence electrons. If you take out some of the silicon atoms in a material and replace them with arsenic, you now have extra valence electrons. In our model, that would look like having our valence band, but then some of these additional valence electrons actually exist at the higher energy space up in the conduction band. That makes our conduction band right next to where our valence electrons are, which makes it much easier for this new mixture material to conduct electricity, since that valence band is right next to the conduction band. This kind of material is called an N-type semiconductor. Mostly because it's got extra negatives, which makes it easier to get towards that conduction band. If we dope the silicon with indium instead, indium only has 3 valence electrons. And adding in the indium will effectively create holes in the valence band. And that will make my model of our molecular orbitals look a little different. Our valence band will be a little smaller, and that conduction band actually comes down to where the molecular band is and kind of overlaps with it. and that makes it much easier for our valence electrons in the valence band to pop into a much closer conduction band. This kind of material is called a p-type semiconductor. For the idea that since we created a hole where electrons used to be, that it would be considered positive. And that's really all you need to know about metals, semimetals, and conduction bands.